In the last lecture, we were discussing about the engineering or specialty polymers. We are discussing about the aliphatic as well as aromatic polyesters, PET, PBT and other polyesters. Now, in those PET and PBT, some part of the repeat unit was aliphatic and other part of the repeat unit was aromatic. Now, a polyester can be made of fully aromatic, that means both the acid part as well as the alcohol part could be aromatic, that is known as all aromatic polyester, known as polyarylate PAR, all aromatic polyester. Now, this all aromatic polyester can be prepared by polycondensation of bisphenol A and mixed phthalic acid. This is the bisphenol A moiety, this is the bisphenol A moiety, and this having this up to this O and this O here. Now, and this is the diacid part. This is a mixed phthalic acid. Mixed phthalic acid in the sense that the linkage linkage of two carboxyl groups to this aromatic ring can be either at the para position or at the ortho position or at the meta positions. That means 1,2 linkage or 1,3 linkage or 1,4 linkage. Any of these 3 linkage can be there. So, that is why it is shown like this. So, this is a mixed phthalic acid. When that mixed phthalic acid is condensed in melt condition at high temperature with bisphenol A, it leads to all aromatic polyesters. Here you see no aliphatic methylene units or methylene linkage is there. Fully the entire chain contains phenyl ring. In between two carboxy phenyl ring, here ester group is there, and here since bisphenol A moiety is there. So, bisphenol A moiety contains one carbon atom between two phenyl rings, and this carbon is linked to two methyl groups. So, that is a very good engineering polyester. Here, unlike PET, polyethylene terephthalate or polybutylene terephthalate, this type of polyarylates is amorphous and it is not crystalline and has and shows very good clarity and provides high heat deflection temperature, and its glass transition temperature is quite high, 150 to 200 degrees Celsius. This range is given because of this mixed phthalic acid moiety, presence of this mixed phthalic acid moiety. From one linkage to other linkage, this glass transition temperature of the polymer varies, and this polymer is stable to UV radiation and it provides inherent resistance to flame, or that means fire retardant polymer, and shows very good electrical properties. Since there is no ionic groups present over here, electrical properties of this polymer is good, but oxygen atom is there, but it cannot be fully resistant to high voltage electric field, but at low voltage this polymer shows good electrical resistance. Outdoor applications of this polyarylate include solar collectors, safety devices, and that is also used for construction purpose, transportation purpose. Plastic parts for electronic and electrical hardwares are also made from these aromatic polyesters, polyarylates, for example, lighting fixtures. So, this polymer is also a very good engineering special type of polymer, specialty polymer, special polymer having very good thermal resistance property and dimensional stability at high temperature, resistance to UV and flame retardance characteristics, etc. Other example of such polyester is polydimethylene cyclohexane terephthalate PCT. Polydimethylene has a methylene group is here, methylene group is here, and these 2 methylene groups are linked to a cyclohexane ring, and this is the actually alcohol part. This is the alcohol part, and this is the acid part. Here aromatic link is there, one cyclohexane link is there, link is there. So, this dimethylene cyclohexane terephthalate PCT has high thermal stability and finds applications in some electronic components like PET, polyethylene terephthalate. PCT crystallizes slowly, PET crystallizes, PCT also crystallizes, but slowly, and so addition of some nucleating agents, and if the molded item in hot condition, if that is cooled by oil, cold oil, that means this, if this mold is cooled by circulating cold oil, that can develop crystallization in the polymer. So, during processing of that PCT, some nucleating agent as well as hot oil cooled mold facility should be used to process PCT in a reasonable time scale. Still there are more engineering polyesters available, and those have already developed and commercialized. Now, instead of one phenyl ring, there could be more than one phenyl ring, say naphthalene ring is there. In this naphthalene ring, 2 carboxyl groups are attached, that is known as naphthalene dicarboxylate. Naphthalene dicarboxylate, this is a symmetrical molecule, and here this naphthalene dicarboxylate can be copolymerized with DMT, dimethyl terephthalate. In fact, when PET or PBT is manufactured, in that case DMT, dimethyl terephthalate, is one of the raw material instead of terephthalic acid. Terephthalic reactivity of terephthalic acid is not good. That is why this DMT is used to manufacture PET or PBT through ester interchange reaction. Here also, in case of this polymer using naphthalene dicarboxylate based polyester, this is also done through ester interchange reaction. So, DMT, if this copolymerized with DMT, this acid part, DMT is also another acid part, and alcohol part would be different. So, one can make a copolyester, that means in the polyester this NDC as well as terephthalic acid moiety will be present. Terephthalic acid moiety comes from this DMT, dimethyl terephthalate, through ester interchange reaction. Such type of copolyester, due to the presence of this naphthalene ring and one phenyl ring, that polymer shows better barrier properties and better heat resistance for bottle and packaging applications. Or this naphthalene dicarboxylate can also be polymerized with ethylene glycol. To yield polyethylene naphthalate, PEN, PEN, polyethylene naphthalate. So, we have seen PET is prepared by reaction of ethylene glycol with DMT or terephthalic acid. Here naphthalene dicarboxylate instead of terephthalic acid can be reacted with ethylene glycol to form polyethylene terephthalate, polyethylene naphthalate. This polyethylene naphthalate is a good polyester. This PEN can be extruded as well as blow molded for making bottles or hollow items. This is the formula of the PEN. So, this naphthalene moiety, naphthalene structure adds to the rigidity of the polymer in the backbone, and this ethylene moiety contributes to the flexibility of the polymer. So, rigidity and flexibility, these two make a combination of properties like say toughness. It can produce a very tough polymer. That is why this polyethylene naphthalate shows better mechanical strength, higher heat and chemical resistance, better dimensional stability, thermal stability, resistance to ultraviolet radiation, and resistance to hydrolytic degradation in presence of acid and alkali, and improved barrier properties compared to polyethylene terephthalate. So, this pen can compete with PET. PET is made from a single phenyl ring containing acid, that is terephthalic acid or DMT, whereas this pen contains naphthalene ring. So, due to the presence of naphthalene ring, it shows improved properties over PET, polyethylene terephthalate. So, these are about these polyesters, engineering polyesters containing phenyl rings, containing cyclohexane rings, containing naphthalene rings. Now, let us see another class of polymer, engineering polymer or specialty polymer, is polyimides. So, today we are discussing about the specialty polymers, starting from polyamides, polyacetal, polycarbonates, polyesters, then polyimides. Now, these polyimides are a class of polymer having this imide linkage, This part, this side is aromatic, this side is also aromatic in the polymer backbone. So, a polymer is formed through such linkage. Nitrogen is connected to 3 different functional sites. If those 3 sites are all aromatic, we get an aromatic polyimide. Aromatic polyimide. One should not confuse with aromatic polyimides with aromatic polyamides. This polyamide contains this linkage, amide linkage CONH, whereas polyimides contain this imide linkage. This is imide linkage. So, if there is presence of amide linkage, we call it polyamide or called nylons, aromatic nylon or aliphatic nylon, and if there is imide linkage, we call polyimide. Now, there can be possibility of many different polyimides depending on the groups on this side and depending on the groups on this side. Let us look into different types of polyimides possible. These polyimides are high temperature resistant polymer, as well as they are resistant to solvents and chemicals. Now, one polyimide can be made from a compound which is known as pyromellitic dianhydride. This is a pyromellitic dianhydride. Now, when water molecule is removed from the 2 carboxyl group, we get an anhydride. On hydrolysis of anhydride, we get diacids. So, this is an anhydride ring. This anhydride ring can be obtained by hydrolysis, forming 2 carboxyl groups. This side also, this anhydride ring can be obtained by hydrolyzing this anhydride ring, and we will get 2 carboxyl groups. So, basically it is a tetrafunctional monomer. This pyromellitic dianhydride is a tetrafunctional monomer. This tetrafunctional monomer in the form of anhydride or tetracarboxylic acid, when it reacts with a diamine, this is a diamino diphenyl ether. At the 4 and 4 prime position, 2 amine groups are present. So, this is a 4 prime diamino diphenyl ether. This contains these 2 aromatic rings. In between 2 aromatic rings, there is the oxygen linkage. Now, there is a purpose of using such type of monomer, because the presence of this oxygen atom over here, it contributes to the flexibility of the polymer backbone, because there can be rotation around this oxygen linkage. So, the polymer will be flexible. So, if this here you see the difference between amide and imide, this amide can also be formed by reaction of a amine group with a carboxyl group. Since here 2 hydrogens of this amine group can be taken away by this anhydride group, that means this oxygen will be taken by these 2 hydrogens. So, water molecule will be released, and one linkage between this carbon and this nitrogen will occur to form that amide linkage of this type, amide linkage. So, when this pyromellitic dianhydride reacts with such diamine, aromatic diamine, this is a kind of aromatic diamine, it can be one diamine instead of this part. If this part is removed, one can have this amine linkage at this position, but purposefully this ethyl linkage has been put over here in order to contribute to the flexibility of the polymer. So, when these 2 monomers or these 2 chemical compounds are allowed to condense, they condense at this position, eliminating a molecule of water, one gets a polymer. This is the repeat unit of the polymer, and this is the imide ring. This is the imide ring, N attached to carbon, CO group, here N attached to this CO group, and this N attached to this phenyl ring, this attached to another phenyl ring through oxygen, and this way it repeats. So, this is the repeat unit formula of Kapton, a polyimide made from pyromellitic dianhydride and diamino diphenyl ether. This is one engineering polyimide in the name Kapton. This Kapton is made in the form of film. Typical use of such Kapton polymer, polyimide polymer is found in electronics field as sleeve bearings, as valve seatings, and as the matrix component of a graphite composite. That means, carbon fiber reinforced composite. So, one can use Kapton as the matrix resin, continuous phase resin, and fiber can be made of graphite or carbon fiber or graphitic fiber or graphite fiber. So, carbon fiber reinforced polyimide resin can produce a very high performance composite that is used as compressor vanes in jet engines and other aerospace applications. So, you can understand the behavior or characteristics of this kind of polymers. So, these vanes can be made of metals. Those metallic parts are replaced by this type of composite, which is made from carbon fiber reinforced polyimide Kapton. There can be other way of synthesis of this polyimide. Basically, this polyimide synthesis is a two-step process. Polyimide synthesis is a two-step process. In contrast to synthesis of polyamide nylon, nylon is synthesized by reaction of a amine group with a carboxyl group, acid amine or acid base type of reaction there. Now, in this case, this pyromellitic dianhydride, it is the basically it contains two carboxyl groups. When it reacts with this amine group of the diamine compound, that is actually that reaction is carried out in presence of a solvent, say N-methyl pyrrolidone NMP. Now, these two reactive chemicals are dissolved in NMP and they are heated at 30 to 40 degree Celsius. This amine group condenses with this. Of course, it should be done in an anhydrous condition. So, this will condense to form one amide linkage over here, leaving behind one carboxyl group free. Here you see on the both side of this PMDA, two carboxyl groups are made freed and two amide linkages are formed. This kind of intermediate precursor is known as polyamic acid. Now, this polyamic acid made by the reaction of PMDA and this diamine, this is soluble in N-methyl pyrrolidone solvent. Okay. Then, in the next step, this is the first step of polyamic acid precursor formation. After this precursor is made, then that is heated slowly to remove the solvent. Solvent will evaporate out. Then beyond 150 degree, slowly this amic acid, this amide group will condense with this carboxyl group, eliminating a molecule of water, one H from this NH and OH from this carboxyl group. So, one molecule of water will be eliminated out from here, and here also another molecule of water will be eliminated from OH and H. So, two imide linkage will be formed. Here you see this imide linkage, this this imide ring has been formed over here, imide ring has been formed over here. This is known as polyimide. This is the repeat unit formula of polyimide. Now, why this is necessary? Why these two steps are necessary? Although polyamides are synthesized by melt polycondensation of a diamine and a diacid, but the polyimides cannot be done by such melt polycondensation process, because once some imide linkage is formed, actually this imide ring is formed, this imide ring containing polymers does not melt, rather to melt these polymers, if the temperature is increased, that undergo degradation or pyrolysis. So, this the intermediate will be pyrolyzed instead of melting. So, such type of polymer synthesis cannot be done through melt polycondensation, rather they should be prepared through a precursor stage, that is polyamic acid stage. Actually, this was done after facing the problem of degradation or processability. These polyimides are not processable by melting, or they are not melt processable. So, the processability of polyimide is very poor. Once a imide ring is formed or once a polyimide is formed, this is neither soluble nor fusible. So, neither it can be dissolved in a solvent nor it can be melted to reduce the viscosity, to make it flowable or to make it fluid. To overcome that problem, people have developed this polyamine acid intermediate precursor step to form this polyimide, but one cannot avoid the use of this organic solvent. This is a highly polar solvent, aprotic solvent, and this is used for making this polyamide in the laboratory or even industrially. So, whatever device is to be prepared, whatever object is to be prepared, that should be prepared with the help of this polyamic acid. Say if one wants to make polyimide film, that polyimide film can be made through this polyamic acid. This polyamic acid is dissolved, remains in NMP solvent as solution, then that can be cast as a film. Slowly that casted film, the solvent is removed, then followed by heating that film over at high temperature, gradually stepwise in increasing the temperature from 150 to 250 degree, sometimes up to 300 degree, that leads to a polyimide film. So, fully cured means fully imidized. This is fully cured, this is not fully cured, this is not imidized, here it is imidized. So, it is called fully cured or fully imidized. Polyimide is insoluble in solvent, infusible also, and has high temperature and oxidative stability, good electrical insulation properties and resistance to high energy radiation like ultraviolet light. Let us look into other types of polyimides. Say this is a thermoset polyimide. Now, previously the previous polyimide, say Kapton, that is not a thermoset polyimide, although it is insoluble and infusible, but we cannot call it thermoset. The polyimide even can be converted to a 3-dimensionally cross-linked network polymer, that means thermoset polyimide. That polyimide can be made if some reactive group, say like acetylene group or imide group, maleimide group at the end chain end of the polymer is present over there, that leads to cross linking or further linkage of this polymer to form a thermoset structure. Now, in this case, this name of this polymer, basically this polymer, the formula you see this formula, the name of this polymer have showing this formula is thermid. It is a kind of thermoset polyimide, where this R stands for a carbonyl group, either a carbonyl group CO or a hexafluoropropane having 6 fluorine atoms functionality, say CCF3 whole 2, and R prime represents the following aromatic group. So, R can be CO, hexafluoropropane or CCF3 whole 2, and R prime it should be either of these R should be 1 prime, it is mistake over here. So, this R prime should be aromatic linkage like this, aromatic groups like this. So, this type of polymer is prepared by heating a fully imidized polyimide pre-polymer having a reactive functional group at each end, like say in this case it is acetylene group present here and here acetylene group, that can react with another pre-polymer thermoset polyimide. Thermoset polyimide is particularly suitable for structural composites, as you have seen in the case of Kapton, matrix and carbon fiber. Here also this polymer can also be used as a matrix along with graphite fiber or carbon fiber that can give high performance structural composites, particularly for aerospace field application. There is a comparison of in this table compares the properties of polyimide Pi, polyether imide PEI and polyamide imide PAI. The glass transition you see is higher than that of polyether imide for higher in Pi than polyether imide. Heat deflection temperature at 1.82 megapascal pressure is high for polyamide imide. Amide imide means a polymer having both amide linkage as well as imide linkage. A polymer in this case of PEI, it is having a polyimide linkage and oxygen linkage, ether linkage, and it is purely polyimide. Okay. And water absorption for these polymers is very good for this polyether imide than polyimide or polyamide imide. Tensile modulus is quite good for polyamide imide. Tensile strength is highest in case of this polyamide imide, and elongation at break is for elongation at 20 degrees Celsius at yield, and at yield this is at yield and this is at break. At yield is quite low for this polymer, at break it is little higher. It elongates to more length at during breaking, and yielding starts below before that. So, yield value is elongation is lower. Flexural modulus is highest for polyamide imide. Flexural strength is again for other two polymers are not available. This for polyamide imide it is 241 megapascal. Impact strength again at two different this is isotope impact strength either in notched condition or unnotched condition. This is highest for this polyamide imide. Another case of thermoset polyimide is known as name is PMR 15, where this R is when N is about equal to 2, this R has the following aromatic structure. That means, here R is replaced by this huge aromatic link containing this imide linkage and ketonic linkage. So, it is a kind of high performance polymer having huge number of aromatic linkages, as well as the end of this polymer chain contains this reactive non-bonding functionality, ethylene non-bonding functionality. This is reactive group. So, these reactive groups at the two ends of the polymer chain, where inside of this chain contains such huge aromatic group. So, they react further to develop linkage with intermolecular linkage, forming a cross-link type of structure and leads to a thermoset polyimide. And such type of polymer has found wide application as matrix resin for again this graphite composites for aerospace applications. So, it appears that these polyimides, Kapton or that thermoset, different thermoset polyimides, as I have shown you the examples with the structures and formulas, they find very high performance, strong, thermally stable, high strength, high impact resistance, high flame resistance matrix resins for making composites to use in the aircraft structures or aerospace structures. We can have further better polyimide if we take this kind of monomer. This shows excellent thermal and thermo-oxidative stability if people can use fluorinated dianhydride of this type of structure. Now, here this methyl groups, hydrogens of 2 methyl groups are replaced by fluorine atoms. So, this polymer is known as 6-FDA polymer, 6-FDA polymer having hexafluoro linkage, hexafluoro functional groups, 6 fluorine containing polymer that leads to a polyimide. So, polyimide with fluorine atoms also. So, it adds to further chemical stability. So, this can perform at very harsh environment at high temperature, or one can use fluorinated diamines such as this formula, diamines having 2 amine group at the 2 ends of this chemical compound. At the middle, methyl groups, hydrogens of methyl groups are replaced by fluorine atoms. So, this is known as fluorinated diamine, name is 2,2-bis 4-aminophenoxyphenyl hexafluoropropane. So, this polymer leads to very excellent thermal and thermo-oxidative stability for aerospace applications, for making composites in aerospace use. Let us look into polyamide imide or polyether imide. Now, to improve the melt processability of polyimides, because I mentioned that melt processability of polyimides are inferior, and that can be improved, provided the basic imide structure can be combined with more flexible aromatic groups, for example, aromatic ethers and amides. Here you see this imide linkage is there as well as amide linkage is there. So, polyamide imide, polyether imide. So, here you see this polyamide imide, this is polyether imide. So, here this is a polyimide having ether linkage, this is a polyimide as well as amide having ether linkage. So, here it shows the tailorability of such polymer materials depending on the requirement of properties, say thermal properties, mechanical properties, chemical resistance properties, radiation resistance properties. Those can be developed by selecting a suitable combination of reactants, suitable combination of functional groups along the backbone chains, say can be aliphatic, can be aromatic, can be ether linkage, can be imide linkage, can be amide linkage, can also be substituted with fluorine atoms. Now, both this polyamide imide and polyester imide, polyether imide, they have high heat distortion temperature, means they are rigid, dimensionally rigid at very high temperature, provides very high tensile strength, high tensile modulus. One advantage of this polyamide imide and polyether imide over Kapton. Kapton is produced from the reaction of pyromellitic dianhydride and diaminodiphenyl ether are their lower water absorption, which is especially important for composite application. So, it shows that this such type of polyamide imide or polyether imide shows further less water absorption than that of Kapton, and so applications of such polyamide imide and polyether imide include high performance electrical and electronic parts, because where this moisture absorption is a deterrent to these applications. If there is moisture absorption, the electrical or electronic conduction or resistance properties are highly affected. So, in these cases this water absorption should be as minimum as possible or no. That is why these type of polymers were developed over Kapton. Kapton is a very good insulator for electrical applications, but over Kapton this polyamide imide and polyethylamide are further better polymers. They are also suitable for making microwave appliances and under the hood automotive parts. Now, we were discussing about polyimides. Now, here is an example of a polymer known as polybismalimides. That means, some malic anhydride has been used as one of the reactant to form a polyimide. In case of Kapton synthesis, you have seen that a dianhydride was used. That means, two anhydride groups were attached to a phenyl ring. Here there is no phenyl ring, but malic acid when it is actually water molecule of malic acid is removed, one water molecule is removed, it forms an anhydride. That malic anhydride can react with a diamine to form an imide, keeping this structure. So, this type of polybismalimiide, trade name is a commercial polymer, trade name is Kerimid or Kinel. This is possible. There can be other polybismalimides obtained by Michael addition of diamine. Michael addition of diamine to the unsaturated sites at the ends of a bismalimide having a structure similar to. So, here this bismalimide in this bismalimide, this maleimide structure is present at the two ends having unsaturated sites. This is one unsaturated site, here is another unsaturated site. So, that can be that was exploited to form polybismalimide by Michael addition of this is the diamine, to the unsaturated sites at the ends of a bismalimide having a structure similar to this. Now, these polybismalimides are used as composite matrix resin, for making composites for filament binding and making laminates, for making friction pads, for making gears and bearings. Now, let us look into another nomenclature of polymers. Ladder polymer, a polymer which looks like a ladder. This is the steps of the ladder this is ladder. That means, it can also be called as double strand polymer or this type of polymers having such configuration can also be called as multi-strand polymer. What is the speciality of this multi-strand or double strand polymer or ladder polymer? In contrast to a single strand polymer, say polyethylene, the formula can be like this, having carbon chain backbone, or it can be looked like this, a backbone made of carbon atom only, and valencies of carbon are satisfied with hydrogen atoms. Now, this is a single strand polymer. Now, if this polymer is exposed to thermal or radiation environment, what will happen? That thermal or radiation energy can cleave anywhere of these primary covalent bonds, that can cleave, or that can cleave also these things. So, the existence of the polymer or the identity of the polymer is lost due to such cleavage by that thermal energy or radiation energy or any chemical energy. That polymer becomes unstable. Now, in this case, having double strand or multi strands, this is a one line, this is another line linked to, these two lines are linked with the intermediate linkage. These looks like cross link bonds. So, if there is some chance of breaking at this site, the polymer will make its identity, will maintain its identity, continue its identity. Even if there is simultaneous breaking at another place here and here, still the identity of the polymer can be restored, or even there is breakage over here simultaneously, still the identity can be restored by the presence of other bonds. Here is the importance of such double strand or multi strand polymers or ladder polymers. Why they are called ladder? Because it looks like ladder like, their configuration look like ladder like structure. Such ladder polymers are formed by incorporating highly fused ring backbones such as polyimidazopyrrolones, showing extreme high temperature stability, as I explained through this sketch. Even if there are breakages, it maintains its identity. Now, if you look into this formula, this structure, this is a polyimide, or this is not a polyimide, but imidazopyrrolane, imidazole imidazole group is there, imidazole group is there. Here you see this is a line, this is another line, and these are connected, these two lines are connected by these linkages. These are primary covalent bonds, primary covalent bonds. So, this looks like a ladder type of structure, and they shows extreme high performance properties of thermal stability, radiation stability, etc. And these polymers are capable of withstanding temperatures in excess of 500 degrees Celsius. Let us look into other categories of polymers, ionic polymers known as ionomers, that means polymers containing ionic groups. Look at these three different formulas A, B and C. This is actually ethylene, polyethylene, ethylene repeat unit. This is methacrylic acid repeat unit. This is sodium salt of methacrylic acid. So, as you move from this formula to this formula, here you see this hydrogen is substituted with this carboxyl group, another hydrogen of this carbon is substituted with methyl group. So, this ethylene has been converted to methacrylic acid. When methacrylic acid is reacted with sodium hydroxide, it forms a sodium salt. So, this is a sodium salt of methacrylic acid. So, polyethylene can be converted to a ionic polymer methacrylic acid or acrylic acid, okay, and salt of acrylic acid. So, this group is ionizable, this portion is ionizable, that is why these polymers are known as ionic polymers. Ionic bonding provides a tough material because there will be ionic bond, intermolecular ionic bond through these sides. So, that increases the toughness of the material, often used for covering golf balls as replacement of gutta percha, which is a naturally occurring polymer having trans configuration as in contrast to cis configuration of natural rubber, and these are used in packaging applications such as a coating for safety bottles, to store hazardous chemicals, and in the manufacture of automotive bumper strips and guards. There is one excellent commercially available ionic polymers or ionomer known as Nafion. This is nothing but a perfluorinated polymer, having all the hydrogens of this repeat unit are replaced by fluorine atom. This is known as Nafion. This Nafion shows selective permeability to ions for use in the production of chlorine and caustic soda by electrolysis of salt solutions. This Nafion is also used for gas separations, because this is semi permeable membrane or permeable membrane to some extent for some material, some compounds. This is used in organic electrosynthesis, used in fuel cells, used in electrodes preparation, used for the separation of amino acids, used also as a device for controlled drug delivery, and also used in biosensor used for making biosensors. Polyaryl ether ketones is another class of polymer. This polyaryl ether ketone is made from potassium salt of hydroquinone. This is the potassium salt of hydroquinone that is reacted with 4,4-difluorobenzophenone, okay, and it forms a peak polyether ether ketone. This polyether ether linkage is there, ketone group is there having aromatic groups. This polyether ether ketone shows high solvent resistance, good impact strength and good thermal stability, and shows a continuous working temperature, used temperature 260 degrees Celsius, used as thermoplastic matrix for graphite composite, solvent resistant tubing for chromatography, wire and cable insulation for hostile environment, and as magnetic wire coating. Some properties of PEEK are listed in this table. Glass transition temperature is quite high, 143 degree, heat dissipation temperature 148, and water absorption is quite low, almost negligible, 0.15% at 40% humidity. Solubility parameter is high, tensile strength 91 megapascal, elongation at break at 23 is 150 megapascal, is quite high, flexible modulus is also high, 389 gigapascal, impact strength is 1388 joules per meter. Polyorganophosphagene is a polyphosphagene polymer, this is the formula, and this is a low temperature flexible elastomer. Two glassy materials can be fabricated in film and fiber form. Potential applications include elastomers, coatings and biomedical uses. High performance fibers are made from this diphenyl isophthalate tetraamino biphenyl. This is actually polybenzimidazole. This polybenzimidazole is amorphous with high temperature stability in excess of 400 degrees Celsius and excellent chemical resistance. This polybenzimidazole burns only in a high oxygen content atmosphere containing 48% maximum 48% oxygen. Applications include many of those for which Kevlar may be used. That means, in place of Kevlar this polymers can also be used, including flue gas filtration of chemical industries and generally as a substitute for asbestos. High performance fiber, other high performance fiber say this polyphenylene benz bisthioazole, this thiazole, bisthioazole, polyphenylene benz bisthioazole. Photoconductive polymer, this poly-N vinyl carbazole, photoconductive polymer, it becomes conductive when illuminated and used in xerographic. When illuminated means when it is exposed to light, it becomes conducting in nature, electrically conducting in nature, and that is used in xerographic copier, laser printer and duplicator industries. This photoconductivity is attributed to the ability to generate fluid charge carriers or electron holes by the absorption of radiation, electromagnetic radiation, and subsequent transport of these carriers to the electrodes. Amorphous polyvinyl carbazole has a glass transition of high glass transition temperature 227 degrees Celsius and density is 1.184 grams per cc. Thank you very much.